Harish here. Harish Doraiswamy is from NYU, the Center for Data Science. This is the last time he came. We also have a CDS now, but it's different. So Harish is a research scientist at NYU at the Center for Data Science, but he's also affiliated with the Computer Science and Engineering Department. And he's been spending the last 3 to 4 years there, working a lot with urban data, right, and trying to bring his expertise on visualization, data analysis, right, topological methods, and also databases to bear on better understanding urban data. So, kind of redesigning New York. So you will see a lot of pictures of his work here. So before going there, he graduated with a PhD from this department. He also did his master's here. And we look forward to listening to him talk about, I think, urban.
No, actually,
not talk about that.
I'm not going to talk about urban.
We talk about a lot of urban data.
Thanks, Vijay. Okay, so yeah, I've been at NYU now since end of October, end of 2012. So it's almost close to. There's a green light here. It's on. Okay. Yeah, so I've been at NYU for more than 3.5 years. I'm audible. The light is on. Okay. And being New York, we started getting a lot of data from the city, and we started working with the data. And in this talk, I'll briefly start with the kind of work I've been doing, and then finally focus on this one of our recent works, which is called data polygamy. And I'll come to why it's data polygamy later on, right? So there's a lot of exhaust from cities. I mean, a lot of data, and especially in the last couple of years, people have been collecting data. There are cheap sensors available, so lots of data is being generated, and even city governments, they're collecting it and making it open, right? So these are like data about the infrastructure. So here you have something like the taxis, public transport, or the subway, New York City subway, or the city bikes. You also have data about the environment, more like weather data or energy consumption. And you also have, of course, the social media data. So here's data from Flickr or Twitter, which is openly available, or at least part of it is openly available, and many other social media, right? And in US alone, I think NYC started it, and soon a lot of other cities caught up. They have this open data initiative using which they are collecting all this data and making it open for people to play around with. In a way, there's so much data being generated, they have no idea what to do with it. So they're just giving it into the hands of people and saying how it can be useful for us. And it's not just US. There is also data.gov.in over here, which is giving open data. There's a similar initiative in Brazil, France, Finland, and a lot of other countries, right? So overall, you can think of this as something like you have this urban environment, which is generating a lot of data. So if you think of the urban environment as a complex process or a complex program and generating this output, what we have is the output, the data. And one of our big or the broader goals of our work is to try understand the city using this data. How can we make sense of all this data, look at the interactions between different data sets? And doing this can, by understanding the city better, we can develop better infrastructure and improve the lives of citizens, and also make city more sustainable, more green, and whatever it is other people want, right? So I'll start with the kind of work we have been doing over the past 3 years. And it all actually began in 2012 when we got the NYC taxi trips, right? So this is, so this data, what it, the Taxi and Limousine Commission gave us this data for, I think, 3 years at that time. And each year there were approximately 175 million trips. And it had a lot of interesting features, like there were 2 spatial attributes in the data. It's like the pickup and drop off locations. You have time, and you have other attributes like fare and so on. And this data it was just amazing looking at the large amounts of data, which is so different from the commonly available data sets. So until then, most of the available data sets were simple tables without much space involved, or even if the space was there, it was coarsely aggregated. But here we had fine-grained resolution in both space and time, and that got us actually excited. And over the course of these 4 years, I don't know how many of you are familiar with this data became our version of the Stanford bunny, right? So this is like a common data set used for a lot of rendering papers and graphics, or it's also equivalent to the Lena in the image processing. So looking at it from different aspects gave us a lot of new insights. And so this is like our test bed, literally. And so when we got this data, the first thing we kind of did was, let's just visualize it. There were even challenges in visualizing this data. It's large, right? So let's visualize it and see what it gives us. Let's just try understanding the data a little more before going ahead with it. And to do that, in our group, we developed this visualization software called Taxiways. And yeah.
About how large the data was in terms of memory, or also in terms of how complex.
Okay, so in terms of memory, I think 1 year worth of data approximately took up, if I'm not mistaken, it was given as CSV files, which took up around 30 to 40 GB of space. And like I said, it has 175 million trips, and the attributes, there were total of, I think, 8 or 9 attributes, which was the pickup location, which is lat long, drop off location, which was again the lat long, pickup time, drop off time, fare, tip, how the fare was paid, whether it was by card or cash, and then distance. So because more often than not, the shortest distance is never the actual distance taken by path taken by the taxi. So the distance and a couple of other attributes. And initially we got for 3 years. That's 2009, 11, and 12, and then later we got 2010 and 2013. And this was before it was made open. And now the new data sets they keep releasing online, and anyone can download the data. So basically what this tool allowed us to do was generate complex spatial queries. So it's easy for user to create these queries and just say, draw some polygons of interest and look at what are all the trips that happen, and also maybe look at the distribution over different time steps. And here we are showing there's a number of trips, but instead you could also look at other attributes like fare or tip that happens. And you can keep creating more and more complex queries over here, right? And typically, without such a interface, it is very difficult to go over this data. I mean, so even a simple SQL query saying something along the lines of, find me all trips from one location to another location is quite complex. And since the spatial part of SQL was added more recently, it's not very flexible either. And talking about SQL, so one of the first things that happened when we started working on this tool was how difficult it was to even execute this query. So here I haven't speed up the video at all. It's the same speed as what we were working on. And so in order to obtain this interactivity for queries, so that was one of the first challenges we had, right? So given this large amounts of data, you have these complex SQL queries that are happening. How would you go about doing it? And the first thing we tried obviously was to try databases. They have been around for 30 years, so it should work, right? What we see is basically these are 4 simple queries of the sort that we chose different pickup locations and different drop-off locations. And the time periods was more like, it was something like find all trips from say Midtown to the 2 airports in New York on all Mondays of a given month, right? So this is just the query. And the result size of this query was something like 13,000, that's about it. But the time it takes, so this is in Postgres, is on the order of 500 seconds. And this is a commercial database, it's again in the order of 20 to 30 seconds. And really, anyone who is analyzing this data as they keep moving around the polygons the query changes instantaneously and you want to see a response immediately. This, nobody can keep waiting. This is more like I run this query, I have a cup of coffee, I come back, I see the result. Not going to happen, right? And so one of the work that we started doing then was how can we have efficient querying? And so we had this work on using GPU and to have querying using the GPU. And we could actually get these queries in less than 100 milliseconds. So this is 3 orders of magnitude over Postgres and 2 orders of magnitude over the commercial database, right? Oh, so this is how you generate the queries over here. So these are dynamic. I draw this polygon, I keep moving around. Each move is a different query, right? And so here this is pickup, and that would be drop off. And then now what we are doing is we are saying I want just strips from this pickup location to this drop off location. So this is a new query. Yeah, so that is the next step. So this was more like just an exploration tool, which users can, and this was mainly, and this tool is being used by the the Department of Transportation there. And they had this large amount of data. They didn't know how to even look at what this data is giving them, right? So this is just a simple tool that using which you can visualize the data and just explore. This is more exploratory analysis. We are not doing anything automatic right now. Okay. I mean, this was just what we started off with. And so once we have this database, yes, we can now do all these efficient query. But the next question is exactly what you're mentioning is this data is huge and complex. How do I even know where to look for, what to look for, right? And there are a lot of interesting patterns. So when using, again, working with the Taxiways and we were looking at the data from different levels. So this is just a simple plot of all the taxi trips over time for 2 years. And you see these interesting patterns over here. There are extreme drops at some times during the year. So, and it's not just when you look at it in 1 dimension. Say I look at it in 2 dimensions, right? So here what we have is, this is on May 1st, 2011, 4 time steps, 4 hourly time steps of the taxi data. And you can see that just between 8 and 10 a.m., there is kind of a nice gap over here. There are no trips at all that's happening here. So these are that's more like a broader or a global pattern that you see. And this is more like a local pattern that happens for a short period of time in a small area. So the next question we obviously asked was, is there a way we can guide users towards these interesting patterns in the data? How can you go about doing this, right? And we had this work, and I think some of you were here last year when I actually presented this work over here. So we used a topology of this data, and we had event guided exploration, which says that, look, these are potentially interesting features, and then we allow users to, okay, now you can explore this again. So we always have the humans in the loop. So this is like a rare pattern that happens on an hourly basis. This is more like the Halloween parade, or this is like daily patterns that happen, or you can also find frequent patterns. This is like the nighttime trends in New York. So you can actually see these correspond to a lot of nightclubs and restaurants in New York City, right? So, okay. So far, we are like, okay, you can explore a single data set and maybe find interesting patterns and guide users for a single data set. But what's happening now is there are a lot of other data sets coming on. And so is there a way to, again, explore multiple of these data sets and somehow see the relation between them or look at patterns between them, right? And towards that, so we again expanded, and we are working on this Urbane framework. And one of the main goals of this framework is there are so many different data sets coming in. We want to allow users to load this data and explore this data. Again, this is purely an exploratory tool, visualization tool. So this is just a short video. So here you have different data sets that are loaded in what is called the parallel coordinates. And here the user is exploring different neighborhoods. You can filter and see how each neighborhood behaves with respect to different data sets. And you can actually do it at multiple resolutions, right? So here we are looking at it from a neighborhood point of view. Now within a single neighborhood, with respect to buildings, we can again look at how the different data sets vary, and you can kind of try to understand what's happening in the city with respect to using the different data sets, right? And so this is kind of the work that we have been doing, and as we are doing, we are understanding the city more, we are understanding the data more, and there's more and more data that's coming in, which also raises a lot of questions, right? So how can you explain all of these different patterns or whatever that you're seeing? Is there a way you can explain it? For example, so this was something that I mentioned. We have these unusual low number of taxi trips that are happening. So why is it happening? Is it a problem with the data? Is it erroneous data? Or is it something like, or is there some explanation as to why this happens? Can other data sets provide us with this explanation, right? And similarly, a common problem in New York City is, and I think it's common even here in Bangalore, it's like, when it rains, you don't find any autos here. And it's almost similar there. When it rains, it's very difficult to find taxis to go anywhere. So is there something that can be, or is there a way to explain such phenomena? Or again, would a reduction in traffic speed, say someone is planning to set new rules for New York, and so the city planners would kind of ask questions like, would a reduction in traffic speed decrease the number of accidents and maybe decrease the number of deaths caused due to accidents? So what's interesting is all of these kind of questions, it's more like we want an explanation, and we are looking at multiple data sets to see if other data sets or the information contained in the other data sets can provide us with an explanation for this, right? So for example, here, if we have data corresponding to all the accidents and we have data corresponding to the traffic speed, so is there a way we can say whether this is going to help or not? Or similarly, when we have taxis, so with respect to this question, there was actually a recent hypothesis, there was a paper published with hypothesis saying that taxi drivers are more like target earners. So when it rains, they get more fare and therefore they finish early and they go back home early. So is there a way you can test these different hypotheses? Or from looking at other data sets, can you generate hypotheses to say why the taxi trips is so low on these certain conditions or on these certain days, right? So what we are actually interested in is the relationships between, or the interactions or relationships between these data sets. And when you look at these, you can have a single data set being related to multiple other data sets, right? And that's why we say data sets are very polygamous. And so now we are in a position where all the data is available. There's a lot of data available. Half of them might be junk. Half of them might be very useful, right? But to go over all of these data sets, over all of these attributes, it's just too much work, right? And there's of course the problem of big data. And what I mean by big in this context is something like NYC Open Data. I mean, I'm from New York, so I'm going to consider just NYC Open Data from now on, right? There are over 1,200 data sets as of now, and a lot of them, a lot of new data sets are coming up almost every month, right? And more than 300 of them are spatio-temporal. So they have some space and some time involved, which increases the complexity of the analysis. And on an average, there are around, on an average, there are around 8 attributes per data set, right? So just imagine if you are looking for some sort of relationships between even 2 data sets, there are 8 attributes in one, 8 in the other, the possible relationships are 64 right there. How do you know what is good, what is bad, right? And it's, even though on an average it is 8, some of them have something like hundreds of attributes. So the weather data that we have for New York has over 200 attributes. And almost, I think more than 75% of them is not useful, but unless you go look at all of these attributes, you're not going to find out whether it's useful or not. And given this large collection of data, and this large number of attributes, where do you even start if you want to look at it manually? Which data sets do you want to analyze, right? And so in order to do this as a first step towards the analysis, yeah. No, so when I say a data set, it is one particular data set. So it is taxi, all the data related to taxis, right? So there are similar other data sets. It's something like there is 911 calls, or more commonly 911, it's not public, but the 311 calls. So New York has this thing called 311, which is again something like 100, not exactly 100, but to give other kinds of complaints which are not criminal. It's more like you're walking on the street and you see this ice formation, so which is hazardous, you can complain. Or there's too much noise because someone is partying very loudly. People can complain saying that, look, these guys are partying loudly, the noise level is too high, and someone will come and whatever. So you have these 311, so this is 311 data. So this is one more data, which again gives which location and at what time a particular complaint happened, right? Or you have something like traffic data, so which gives us the speed of traffic on different streets in New York over time. So each of these is different data sets, but again, in NYC Open Data, there is a lot of redundancy too. So the 311 data set itself is split in multiple forms and so on. But again, the problem here is without going over this data manually, you're not going to know all of these problems. There is no. I'm not sure how exactly the process is, but there is this company called Socrata, which is doing all the curation, right? And but there it's more like it is different government agencies. Each of them collect their own data, and then they give it to Socrata, who curates it and puts it in a single kind of repository. So there is something there for people to upload their own data over there. I'm really not sure how to do it. I've never tried it. It might be possible. Yeah. Any other questions?
No, this company does it just collect the data, or are you saying that they?
The company doesn't collect the data. It just curates.
They help for these different government agencies to deposit their data
Yes.
in a common place.
Yeah.
But do they provide any services on top of that? Like, if the data is just available in the format that the agency gives it?
Yes, it's more often than not available in the format the agency gives it. They have a few different formats. The most common is CSV files, and then you also have some data. It's more like shape files. So when there's some geometry involved, and then there is. I've even seen data sets with PDFs. So which is there is no conversion done by them. No, and they provide a very rudimentary interface for maybe searching this data and querying this data. And for some of the shape files, you can quickly view the data over a map or overlaid on a map. I think they use OpenStreetMaps for that. Okay, so I don't, well, I haven't personally looked at many of these, and there is another group or other set of people who are actually working on curating this data. I still haven't looked at the data from India, actually. That's something I'm very curious about, which I'm planning to do soon. But at least for New York now, so we have, there is a group that actually worked on improving this curation. So what they did was they took all these 1,200 plus data sets, and then they kind of merged some of them which are similar to have a much more uniform And they also, and in many of these data sets, the metadata is really bad. You don't know what that given attribute corresponds to. So they even did some sort of processing to kind of automatically identify the attributes, and then so it's easier for user to search the data, right? And what I'm more interested in is once we have the data, how can I make sense of it, right? So, so yeah, given these different amounts of data sets and these different attributes, how do you find the different possible and useful relationships between these data sets, right? And that is where we have this data polygamy framework, which was more work done together with Fernando, Theo, and Juliana. So the goal here is simple. It's more like I want to execute this query, find all data sets related to a given data set D. That's it, right? And the goal here is how is this going to help? So given this large amount of data, this would at least guide users on focusing on saying, okay, what are the kind of data sets I should look at? Or if the user already knows that he is interested in, say, the taxi data, right? I can say, okay, find me all data sets related to the taxi data. I know the relationships, and now from here I can start doing a much more in detail analysis on just these select set of data sets. Otherwise, it's very difficult to know what other data sets or what other attributes of the city is going to affect, say, the taxis in a city, right? So for example, if I have something like, would a reduction of speed reduce the number of accidents? I just say, okay, find me all data sets, all relationships between collision and traffic speed. And from this, if I know that, okay, increase in traffic speed has more accidents and maybe is more fatal, then I know, yes, reduction would potentially help, right? Or something like, why is the number of taxis too low? I can find all data sets related to taxi and hope that one of them gives me an explanation of why this happens. And of course, there are many challenges here. The first one itself is, how do you even go about defining this relationship, right? So again, let's look at why the taxi trips are so low. It so happens that when you look at the wind speed for the same time, you see that at the times when it's extremely low, the wind speeds are extremely high, right? So this in a way says that this is not an error, but something due to high wind speeds is causing this. And this actually corresponds to Hurricane Irene and Hurricane Sandy in 2011 and 12, right? So, and what is interesting here is this sort of relationship happens only when there is some event occurring or there is something that is not normal happening in the data set. And at all the other times, there is almost no relation. It's just random, right? So these kind of relationships happen only at certain spatial locations or at certain time periods when something interesting happens. So you need to be able to capture this, right? And if you look at conventional techniques, one of the things that they do is they kind of look at the entire data set. And if you even take the taxi trips and wind speed, you find that it's not at all correlated, right? So it's a problem. So we need a way to define relationships that takes into account both space and time and kind of tries to look at these features. And of course, the next one is the big data complexity. And moreover, more than just the number of data sets, you get data sets in multiple resolutions. There are some data sets which come as zip codes, some as neighborhoods, some as GPS locations. Some it's more like aggregated for the entire city. So you need to somehow take care of all these different resolutions, and even time resolutions are different in a similar way, right? And given the many attributes, and this is just taking the 300 spatio-temporal data sets in NYC Open Data, for a single resolution, there are almost close to 2.4 million possible relationships. So how do you find what is actually meaningful from this whole set of possible relationships? It's like searching for a needle in a haystack. So we need to be able to find some useful relationships from this all possible set, right? And the key idea in ours is to use topology to define these relationships. So essentially, it's like I mentioned, there are these interesting features in the data or events happening in the data, and we want to find relationships between these events of some sort. And we use topology to identify these interesting space and time regions of the data, right? So what do I mean by a topological feature here? Consider some data and think of it as a terrain. So you have space here, and say the value for each point. So assume this is the space corresponding to Manhattan, and each point you have the number of taxi trips that begin, number of pickups that happen, for example, right? And that is shown as the height over here, right? So what you have is some sort of a terrain happening in space in a given time step, right? And you can clearly see there are these peaks that happen at different points, which are potentially interesting. And there are these deep valleys that happen, which are also interesting. So these are captured by critical points of this, if I can think of this as a function, which is defined on a plane. So these peaks and valleys are captured by the critical points of the function, right? Yes. So this is more like a toy example. I'll show you real scalar functions in a couple of slides, right? So if you can imagine the data set is modeled as a terrain. So this topology, the peaks and valleys, gives us the interesting points of the data, right? And what are the advantages of using this? So one of the things that we noticed is at least a lot of interesting features are naturally captured by the critical points, right? So again, the same example of taxi trips, and you can see that there are a lot of these minima that happen, and these are more like the significant or really deep valleys, significant minimas over here, which can be captured easily by what is called as persistence. I'll come to that a little later, right? So these critical points naturally capture at least some of the features of the data, if not all, right? And the other advantage of using topological methods is features can have arbitrary shapes. Of course, since I'm looking at some sort of events and trying to do relationship between these events, I could also alternatively try some event detection techniques that are common in the data mining community or the machine learning community. But one of the main problems with those techniques are it's computationally expensive, and users more often than not, they define the shape of these events. So they kind of, if you look at something like SAT-scan, for example, scan statistics, they define circular shapes and they look for some events within these circular shapes of different sizes, right? So unlike any of those, using topology, you can have arbitrary shapes. For example, so this is again the 2D figure, and what was actually happening here was there was a bike tour that happens in the 2 time steps. It's called the Fibero bike tour, which happens every year, and at that point, the path corresponding to the tour is blocked to traffic, due to which there are no taxis. And by modeling this as a function and identifying the critical points, you can actually find the path corresponding to the bike tour. And look at the shape, the way it goes. It's like straight over here and it turns over here. Coffee. So it's not any regular shape. You can really have arbitrary shapes for the features, right? And again, when you think of the data, time-varying data as a time-varying scalar function over multiple time steps, you can think of it as a 3-dimensional data, 3-dimensional function. And you can again have events or these topological features that span multiple time steps, right, in a continuous way. And at least the technique that we'll be using, the same technique works on data on any dimension, right? And of course, so this is like a simple 1D over here. So this is like I have data aggregated for the whole city over time. Or instead, this is more like I have data in 2D over time. So this is more like three-dimensional data, and exactly the same technique, the same code will work on all dimensions. So you don't need to keep customizing it for different kinds of data sets, right? And the most important thing, or one of the most important things, is it's also very efficient. So let me. Oh, no. So here okay, no. So each attribute is not a dimension here. So the dimension here is more with respect to space and time alone of the data. And the attribute is specified as a function on the data. Yeah, I'll be going into the details now. So yeah. Moving on to the details. So our framework basically has three major steps. So the first step creates a consistent representation for the data. So all our assumption is the data given to us, which you need to analyze, clearly has metadata corresponding to what the spatial attributes are, what the temporal attributes are, and the types of the other attributes. That's about it, right? So using this, we do a data set transformation which converts this data into a set of scalar functions. The next step uses this scalar functions to identify the most prominent topological features of this data. And the final part of it basically identifies the different relationships based on the topological features and gives you the query, right? So let me go into a little bit of detail here. So like I said, every data set is converted into what is called a scalar function. And simply put, scalar function, or at least the function we are interested in over here, is a domain which is over space and time. And for each point of the domain, there is some function value assigned to it, right? And this domain can be different. Like in 1D, it's like, or like the time series that I showed earlier, the domain is just 1 point for the city. Or instead, I can have something like this. So here I can define a high resolution grid over the city. And then for each of these grid points, I can have a function value which is more like the density of taxi trips, for example, right? So this would be another resolution of the function. Or I can have the spatial domain, which is something like the neighborhoods in the city. And for each neighborhood, I have the number of trips that are there, right? And so you can define this scalar function. And in particular, we define two types of scalar functions in this work. The first one, what we call as the count functions, and the second one, what we call as the attribute functions. So the count function, essentially, what we're interested in is to capture the activity of the entity. So again, taking the taxi example, if I just look at something like number of taxis over space and time, and I can get some sort of densities of taxis over space and time. So this is one type of count function we are interested in. The other type, this is more like why, say I want to answer why the number of taxis are very low, or why it's difficult to find taxis when it's raining. So here we are looking at the unique number of taxis running at any time. So here we are looking at the unique function. It's more like select distinct within a given region in a given time period, right? So these are the two types of count functions that we're interested in. And the other thing is, of course, the attribute functions. So here the goal is we want to capture the variation of what a given attribute says about that data. So here it's like average fare of taxis in a given space and time period, right? So this could kind of give us something like, okay, when there are really high fares, or when you look at whether the average wind speed in a given space-time interval, right? And we compute these functions for all possible resolutions. So like I said, you can have multiple resolutions over space, like you can have something like zip codes, or a high resolution grid, or neighborhoods, or just the city itself. Or even in time, you can have something like you can have an hourly resolution, or a daily resolution, or a weekly resolution.
When you actually represent your example, you work with a uniform representation, like the continuous functions and also discrete functions.
Oh yeah, so the representation of the function is okay. The slide is hidden here, but we represent the function as a graph, a piecewise linear function over a graph. So for example, let's take the neighborhood example for you. So one time step, what I have is I have one node corresponding to each neighborhood over here, and there is an edge between them if the two neighborhoods are adjacent. And you have the same over time, and the same nodes over consecutive time steps are connected. So what we have is a graph representation of the data. And the function is defined on the nodes of this graph. So if I have the average or the total number of taxi trips in each neighborhood, so each node for a given time period, so that would have the function value equal to the number of taxi trips in that space and that time period. And over the edge, we assume a piecewise linear interpolation. Right. So once we have a common representation of the function as a graph over here, the next is how do we identify the topological features. So when I say topological feature for this work, what we are looking at is the neighborhoods of these critical points, and these neighborhoods, okay, so again, this is the same example that I showed earlier, and we have two different types of critical points. So the maxima corresponding to the peaks and the minima corresponding to the valleys, right? So once we have this, what do I mean by the neighborhood of a critical point? So we define the neighborhood based on a threshold, right? So for example, consider some function value, some threshold value over here, and we say all points or all features, all points in the spatial domain above this threshold is the set of positive features, right? So this threshold would define the neighborhood. So in this case, this threshold gives us a neighborhood for these two critical points. Similarly, I can have a threshold for features for valleys, for minima, and this would give us a set of what we call as negative features, right? And each of these features is represented as a set of spatio-temporal points. So here the points is the nodes of the graph. So how do you go about computing these features and these thresholds, right? So let me first say, given a threshold, how to efficiently compute these features. We use the merge tree. It's a topological data structure as an index to efficiently compute these features. So what is this merge tree? Again, consider this function again, for example, and say I am having, I keep varying the function value from the highest value and I keep decreasing it, right? As I keep decreasing, when the function value is higher than the global maximum, there are no components, there are no features, right? As I keep decreasing it, at some point here, there is a feature that is created. And when the function value reaches below, there are two features or two components that are above the given function value. So as you keep going down and track these components, what we get is this tree. And at say some point over here, some saddle over here, two of these features would merge. And at another saddle, they would again merge, and it continues, right? So this merge tree essentially tracks the topology, or in this particular case, the connected components of all the features, or in more formally, the superlevel sets of the data, of the function. Right? And again, like I mentioned before, the data can be in any dimension. And so how do you compute, so given this merge tree, how would you compute, given a threshold, how do you compute the features? It's actually pretty simple. So it's output sensitive algorithm, which is basically I already have the merge tree, and I already know all the maxima in sorted order. And all I need to do is go over the merge tree, start from maxima and go down, traverse down until I hit the threshold. And I just do it for all the maxima that's above the threshold. So in a way, it gives me an output sensitive time complexity for computing the features of the data. So the next question is, yeah, now I can compute, given a threshold, I can compute these features. How do I identify this threshold. What is a good way of identifying this threshold? So for that, what we use what we call the topological persistence of the features, right? So the topological persistence intuitively corresponds to the height of each of these features. So again, think of my traversal as I keep going from say x1 and I keep going down, right? So say x1 is created at a function value equal to 20, and x2 is created at a function value at say 15, and x3 at something like 13, right? And once the function value passes the saddle point, say which is 10, there are two features corresponding to x1 and x3 which merge. So you can think of x3 which was created at 13, function value 13, merges at function value 10, right? Or it's destroyed. Something that's created at 13 is destroyed at value 10. So for each of the features, you have the birth time and the death time, the creation and destruction time. And this difference intuitively gives the lifetime of this feature. And this is what we call the topological persistence, right? So here it would be something like the height of this, the height of this, and the height of this, and so on. Actually, this height goes all the way down, but yeah. And again, using the merge tree, we can compute the persistence efficiently. And what we are interested in is identifying features that have relatively high persistence. I want these to be my features. So for that, we use what we call the persistence diagram. And so this is the persistence diagram for the taxi data and the set of minima. And what it essentially does is it plots the birth time to death time of each of the features, right? So you have some features here which are born really early and die pretty late, some which are born and kind of are destroyed pretty quickly. And as you can see over here, and so the persistence value here is essentially the height of each point above this x equal to y line, right? So you can see that the set of high persistent features form some sort of a separate cluster compared to the set of low persistent features. And we use this insight basically, and this is not just for this data set. This we saw it for a lot of other data sets too. And so we use this insight, and we just do a simple two means clustering over the persistence diagram over here, and we find the high persistence clusters, and we define the threshold such that so in case of the minima, it is the lowest threshold such that all the high persistent minima are features, right? And I can define a similar threshold for maxima as the highest threshold such that all the high persistent maxima are features. Any questions so far? Yeah.
So you can imagine that you have what you have here, right? Plus another cluster which is around 1,000.
So you mean something that is born here and dies really far? Usually, I mean, that case, something that's really high would have an early birth rate. Any high persistence thing would have a. I don't think you can have something that's here which has a much higher.
Well, it depends on the data.
It.
On the x-axis is just some scalar value.
Right. Yeah, it also depends on the data and the distribution over the space as to how far it is and when it is born. But since we are looking at a connected domain in some sense, right? So I would actually expect that would be the global maximum in some sense, because it dies at a much, if you look at it, say a maximum or a global minimum. It's one of the two, right? And a global maximum or global minimum would obviously have the highest persistence and which would then be paired to the global maximum or vice versa. So I really don't think such a case is possible. But well, theoretically, I haven't proved anything, but we have seen this for a lot of data sets, and it's not just here. Even in one of my previous works, so this was done over here using cloud data, we saw similar functionality of all the of the persistence diagram. So, I mean, intuitively, I don't see how it is really possible. While I don't have a theoretical proof, but I think it's not.
And you just think about, the distinction between the size of the feature and what regime is happening.
Right.
So you think of temperature or in this case, I will cost. Right? So also that you have like a feature at low cost interval and also high cost. Both are possible.
Yeah, but the high persistent at the high cost interval would, okay, would actually, no, that would be paired with the global minimum in some case or the global maximum. Yeah, it's going to be someone nearby, so that is going to have a pretty early birth rate. So I really don't see how it can happen, but maybe we can discuss this offline. But that's actually a very good question. So, I mean, there are different kinds of scalar functions that you can define, right? So, at least for this work, we started with the simplest, which is just the count or the density, and then the average values or maybe the min max values, right? The other option is looking at something like the gradient. So, what would if I, instead of defining the count or the density, what would happen if I define a gradient function? What would the peak be or what would the value be, right? So, a peak in that sense would be something like a point where there is a drastic reduction of the function, of the original function, right? So, this would kind of capture in some way something that's smooth versus okay, so let me try to understand your question again. So you're saying there is some, okay, so you're talking about two data sets here, taxi and wind speed, right? Okay, I have not yet come to the relationship between them. This is just a given data set, what are the topological features, right? So the features would be based on the actual function value, right? So what you define the function value would say what kind of features it is. So if I have something which is just starts and keeps gradually decreasing without any high variation or something, so you might not have any features. But if you look at other functions, like you look at the gradient, maybe you can find something interesting with that, right? You could have something decreasing, but the gradient would say when there is a higher decrease, lower decrease, and you could find it, right? So yeah, the thing is, of course, this is not a be all and end all solution. This is just one part of the solution to help towards something. You can obviously keep extending this framework, and I'll come to this later. Okay, so the final step here is how do we evaluate relationships now? So now we have all the interesting features of the data. So we need to evaluate these, identify whether they are related, how they are related, and some way of quantifying these relationships. Right. So first, let's look at relationship between individual features, and we'll use a favorite example again. And let's think of another simple function, which is something like this. So when you look at all the features of this, this has two positive features, one negative feature, and this particular function has one positive feature. And you see that these two features occur at a same spatial location in some sense, right? So basically, like I mentioned earlier, a feature is nothing but a set of spatio-temporal points. And the spatio-temporal points corresponding to this feature intersects with the spatio-temporal points corresponding to this feature. Both are positive. So we say there is a positive relationship when such a thing happens, right? Or let me look at another function, something like this. So here what we have is the points corresponding to the positive, the negative feature of this function intersects with the points corresponding to the positive function of this feature, right, over space and time. And so in this case, we say there is a negative relationship between features. So this way, for individual features between two data sets or two functions, you can define a positive or a negative relationship between them. So basically, in an intuitive sense, what this says is when something is low in one, it is high in the other, or vice versa. Or when something is low for negative, for positive, it's more like if something is high, the other is also high, or when something is low, the other is also low. So yeah, and so now we know how to define relationship between features. So now, given the entire scalar function, two different scalar functions, how do you quantify the relationship between them? So we define two measures to do that. The first one is what we call the relationship score, which basically says how related the two functions are, right? So in this case, whenever there is a negative feature over here, there is more of a positive feature than a negative feature in the other function, right? So this way we say that there is a negative relationship. It's kind of opposite. The other measure that we use is the relationship strengths. So what this says is how often the functions are related. So I can have two functions, which is like whenever there's a feature in one, there is a feature in the other, and it almost always happens. So that way it is like a strong relationship. It's highly related, right? And in this particular case, the relationship is only on a small subset, only along this particular relation or this subset of the whole scalar function of the domain, there is some sort of relationship. So in this case, it's more like a weak relationship. So the relationship strength essentially says how strong or how weak the relationships are. And one more thing that we did, and I'm going to skip it in the interest of time, is basically we also perform a set of restricted Monte Carlo tests to filter coincidental relationships, right? So we find only significant relationship. And so let's go back to the query of interest. Find relationships between D1 and D2 satisfying a given clause. So here the clause can be I'm only interested in positive relationships that has strength greater than some value, or I'm interested in negative relationships, or having a score something and strength something, right? And we only return statistically significant relationships. And so this significantly reduces even the number of relationships that's output. So it's in a way it guides the user saying that these are what data sets are potentially more interesting for you than the others. So maybe you can start looking at this, and then if you're not satisfied, you can go to the others. It's more like guiding them in the exploration process. And I'll quickly go over the experiments. We implemented this framework using Hadoop. We used two data sets. So the first is all the spatio-temporal data sets from NYC Open Data, and the other one, what we call NYC Urban, is a selected set of data sets which we have worked with previously. So we know about the data set, and we can better understand if whatever we find, the querying the relationships we find make sense or not, right? And we can evaluate over 10K relationships per minute. So given any query, you can do this quickly. And on an average, the significant test significantly reduces the number of output relationships, right? And we also have experiments to show that the approach is robust to noise. This is primarily thanks to the use of persistence, which is robust to noise. And we could add some noise to the data sets, and you could still find very similar results. Right. And let me end with some interesting relationships. So let me revisit the questions that I asked initially, right? Would the reduction of traffic speed reduce the number of accidents? So when we do the relationships between collision and traffic speed, we find a positive relationship between number of collisions and the speed, and a positive relationships between the number of persons killed and the speed. So the fatality is also high when an accident happens at a higher speed, right? And coincidentally, quite recently actually, So NYU proposed this new rule to decrease the speed limit from 30 to 25 to actually limit the fatalities during accidents. This was the other question. Why is it so hard to find taxis when it is raining? And so like I said, there was this hypothesis that says taxi drivers are target earners. So I can query for relationships, say, between taxi fare and precipitation, or that's rainfall, and we find a strong positive relationship between rainfall and the average fare of taxis. So this kind of, in a way, says the hypothesis could be true, right? Why is the number of taxis too low? I already showed one example where it's because of high wind speed, and we actually found another example too when we did find all data sets related to taxis. So one of the thing is, even for precipitation, so a couple of them, like this was due to the wind speed. There are these others which are more like due to the high precipitation too. Even when there's heavy rainfall, there is no number of taxi trips, right? And this was again another kind of, this is more like weather and city bike. So in particular, the snow precipitation, the amount of snowfall, and we find something like a positive relationship between snowfall and the duration of each bike trip, which kind of makes sense. And this was a more interesting one. It's more like a negative relationship between amount of snowfall and the number of active city bike stations. And why this is interesting is, one, we couldn't find this at the hourly resolution. But when you increase or rather decrease the resolution to something like daily, you could find this as a significant relationship. And one of the reasons is basically this. So over a larger time bucket, literally, so once the snow is accumulated, then what happens is, especially in a city like New York, there are some areas where they clear off the snow quickly. Some areas they don't, right? So this potentially has the implication that only bike stations in these areas that are cleared are active and not the others. The first one or the second? In some sense, yeah.
So I'm curious. So back to the difficulty of actually finding these directions, right? So you have let's say I don't know the exact numbers here, but we are trying to study some city wide behavior, right? So you want to compare it with all other data, like all other attributes. About 100 attributes, and then you reduce it down to how many before you found.
Oh, so here, so basically for some of these, we just ran the query, find all relationships between all data sets having the absolute score greater than 0.6, right? So it's at least, it's something like at least 80%, the scores go from -1 to 1. So it's at least 80% positive or 80% negative, at least. And strength, okay, we didn't put anything on strength because we wanted to find all possible things. So this was the thing. And we found, so this is with the 9 data sets, right? And if I'm not mistaken, over different resolutions. So for example, so some of the relationships we found with speed and collisions, for example, that's on the 2 dimensions, whereas this one, since the weather we got it as just for the whole of the city, this is more like a 1 dimension. So put together different possible resolutions, we got around, I think, totally around 300 significant relationships. And then we went manually through it, looking at it to see whether it makes sense. So this was more like a qualitative analysis to say, okay, does the relationship find, is it actually useful, or does it just give out something randomly which nobody cares about, right? So that was the main goal of this particular experiment. Okay, so all we focus on historical analysis, on historical data. Okay, so we don't take into account streaming data as of now. So at least this work, the data is already there. I just want to understand what's happening And a lot of planning happens by looking at historical data rather than real-time data. So, I mean, these are long-term plans. So, and well, this shouldn't be surprising. So, the weather data set is the most polygamous. Yeah. That's possible, yeah. I mean, like I said, so this is more like, given the data set, can some sort of explanation be found? And so since this hypothesis was already there and there was actually a paper talking about this, we said, let's test it out and let's see what we find using our approach, right? So yes, this is possible. This is one particular thing. And again, this is like the first step towards exploration. From all this whole data junk, in some sense, you find the small set which is potentially useful. And now the users or the domain experts can do a much more involved and detailed analysis and explore further, right? So this more like helps in filtering and helps you begin somewhere, to start somewhere. Yeah, so right now, no. So that is why we kind of have a slightly coarser time interval. So we look at hourly or we look at daily rather than looking at every minute or every second. So there we really need to consider the offset. So here it's more like behavior in a smaller time range, right? And the offset would actually be very interesting when we look at causality. So right now we are saying there is a relationship, but it's very difficult to say whether A is causing B or B is causing A, or if it is not at all interesting, right? So that is something that we are looking at. That's the next step at what we are looking at right now. So far, at least in causality and a lot of things, like one of the most common things is I think Granger's causality or the lead lag analysis. There are different things that are used from the data mining community or the machine learning community. So all of them work with just time series. They don't include space into effect. So here it's not just the offset in time, there's also the offset in space. I can have an accident right here which is going to affect a neighborhood, right? Or some other part, it's going to affect some set of neighborhood over there. So there's an offset even in space, right? So there is a lot more complications, and we're still not sure how exactly to go about it, but yeah, that's like the next step as to what we are looking at over here. To summarize, what we have here is alternative definition of relationships based on features in the data. We use topology to make it efficient, and we have a scalable implementation, and it's quite. So yeah, the next steps is more like this causality, and then for now we can find certain types of features. So how can you define different other scalar functions to find different set of features? How to handle non-compatible resolutions, or and while using the 9 data sets, we got just around 400 results, making it easy for us to manually go through. But when you use the NYC open data with 300 data sets, we still have around, I think, 20,000 or 30,000 possible relationships across all data sets. So it's difficult even to explore even these reduced set of relationships. So how can you efficiently explore this? Maybe most likely visualization is going to help in this case. Right, right. So, okay, so there are two kinds of analysis, right? So there are some which they know or they have some hypothesis they want to test it. But now it's more like it's very restricted. If you are doing that, and a lot of other domain experts that we are speaking to, it's like it restricts the understanding of data. You miss a lot of important things. And they are now also interested in just exploring these different, just to see what this data gives me. They have no idea. So this is going to help in that case a lot more.
But even so, right? So if I am, let's say, an architect, right, I would be interested in parts of the data, and then there will be obvious parts that I won't care about.
Yeah. So yeah, those kind of filtering.
A certain kind of questions that I would be more interested in. Maybe I don't know what pattern, right?
That's right.
Yeah. That can also help you identify what data sets to pick.
Right, yeah. Yeah, that's true.
You started by discussing something like that. When do you identify data sets are interesting? When do you identify a task is related to a particular data set?
Yeah, that's also an interesting thing. So yeah. Yeah, in that it's going to help a lot more because, I mean, that depends, that's why we have this querying interface, the user can give the kind of queries. So what we did was just said find all relationships across all data sets. But they can obviously restrict it to just say something like find me just relationships. So the architect might be interested in say something like, I don't know, energy consumption. Just find me all the sites or not all the sites. Find me all data sets that are somehow related to energy consumption, right? So that way they know the different kinds of things that can affect energy consumption, and then from there they can then start fine tuning their results or whatever it is. So yes, it's going to decrease it further, but I mean, I don't think I can say that even when you use just a few data sets, it's always going to be very small. It could be large even then, but yeah, it's going to help a lot. The type of land use, there is data set, yes, there is, in New York, there's something called Pluto data. So we can talk offline if you're interested in that. So that's there are other works that I'm doing, working with architects over there where we make use of all those data sets. Right, yeah. Yes, yeah. Yeah, we have land use data, but we don't have historical data. We just have the current land use of New York City. And yeah, of course, thanks to the people at VIDA, which is our group, and a lot of the work here is obviously with a lot of students over there and finding resources. So, and yeah, anyone who's interested, the code, data, experiments, everything's available in our GitHub page. So you can play around with it, add in your own data. It's totally reproducible. All the results in our paper are reproducible. So yeah, thanks. Any questions? Our cloud is internal to NYU. So yeah, that would be even easier, but unfortunately, no.